So now we're sinking our teeth into the meat and potatoes of chemistry. Let me see, what does this look like? It's corner, yeah, we're good. This is good, okay. And how about some lights? Boom. All right. I don't care if you take notes or not. I'm never going to check your notes. I'm never going to check your notebook. So if you want to take notes, great. If you don't want to take notes, great. Whatever helps you learn the material, just understand that everything I say and everything's on the screen, you are accountable for on assessments. So if you have any questions, let me know. This is our first, we're real chemistry. We're getting into it. We're going to talk about nuclear stuff. A whole bunch of today is going to be a review from what you've heard in previous classes with protons, neutrons, and electrons. If you have any questions, stop me right away. Just put your hand up and wave around. It's I got that question now. Because I know how it is. If you pretend you hold on to that question, hold on to it, and hold on to it, and you don't want to sound stupid when you finally get called on, I forgot my question. And you're all you blush and you're embarrassed and it just haunts you for the next 30 years. So if you have a question, just let me know and I'll try to answer it as soon as possible. That way you're actually listening to everything else that goes on. Okay, cool. All right. Now, when it is time for you to do things, I will ask you to use your slates and put work on your slates. But for the most part, it's up to you. I put the entire presentation as a PowerPoint on Canvas. You can follow along if you want. You can type your notes into Canvas, into a Google Doc if you want. You can do it on paper if you want. Whatever helps you learn, I'm on board with that. All right. So if this makes sense to you, give me thumbs up. You're good? Good. If you have any questions, wave your hand around. Okay, because that's the system we're going to use. If you have a question, wave your hand. If you're good to move on, give me a thumbs up. Cool. All right. So this is the study of atomic theory. We're going to talk about atomic theory, what's going on inside the atom, and we're going to talk about nuclear, like what happens with protons, neutrons, and electrons when they have to give up tiny particles. The atom gives up tiny particles. All right, so let's just get right into it. So chemistry lingo, again, all this stuff is review from previous classes. Atoms are the simplest building block of matter. They're the things that maintain or retain the properties of something larger. So carbon, hydrogen, oxygen, nitrogen, and phosphorus, those are the atoms that are in all living things because those are the atoms that make up DNA. They're in everything. Anything living will have those 5 plus whatever else they need to be them. But the simplest building blocks of matter. Now, elements are what we're going to encounter in real life. Sometimes we don't actually encounter a single atom as an element. So there are 7 of them. They are called diatomic, literally 2-atom molecules. So the diatomic molecules are never found in nature alone as just a single atom. They're always going to be bound to a neighbor or in an element or in a compound we're about to talk about. Okay? There are 90 naturally occurring elements. Okay? Everything after 92 is referred to as transuranium, meaning artificial. So on this planet, in this solar system, you can dig up everything up to uranium with the exception of technetium and one other atom that I cannot remember that is artificial. Technetium or technetium or whatever, that's artificial, and there's one more that's lighter than uranium is artificial, and I forgot what it is. It doesn't matter. Oh, promethium. There we go. Technetium and promethium. So those are lighter than uranium, but not found in the solar system. But everything else up to uranium is. Everything after uranium is artificial, made in a lab, like in the video. Okay. So the diatomic molecules, there's a fun little mnemonic to remember the diatomic molecules. I'm going to talk about these a lot because they're really important, and that is Brinkelhoff. Brinkelhoff. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine are never found as a single atom. They are always found in a compound or bound to another one of them as a diatomic molecule. You're never just going to see O. You're always going to see O2 or O3 or Fe2O3. You're never going to see just a single oxygen atom. If there's oxygen gas, like what we need to breathe to live, it's going to be O2. Okay. If that concept makes sense to you, give me a thumbs up. Okay. If anything about that is unclear, wave your hand around. Okay. How can I help?
So why, like, what makes it known that, like, say, like, fluorine, like, how do you know if it's, like, singular or double or triple fluorine?
Like fluorine? Okay, so if you see something, if you see just F, you're like something plus F makes something, that isn't always going to be wrong. It's always going to be F2. Okay. That's what we're talking about. So it's never just going to be F in a chemical equation or a chemical reaction. It's always going to be F2 or something like you might have sodium bound with fluorine. It might be NaF. Okay. So these are valid. This is not. Single F, no good. F2, okay. NaF in a compound, that's okay. So again, a compound is simply something that is made of 2 or more elements. So we say it is a compound when it is made of 2 or more elements. And there are different types of compounds. There are ionic compounds and covalent compounds, and we'll get to that in a little bit in part A3, I think. All right. We move on. All right. Some of you are still madly scribbling, so I'll let you scribble. Just point of tip. If you are trying to write down everything you see on the screen, I have only one question for you. Why? Why would you waste all that time and hand crank? You're like, school is hard, my hand hurts. Because you've been told by bad teachers that you should write down everything. That's just stupid. If something is profound, you're like, oh, that's a new thing. I'm going to write that down. Write it down. If something is confusing, write that down so you can ask later. But if you're trying to copy down everything you see on the screen, very bad idea, because I'm going to start speeding up. Yeah.
So if we did this on our Chromebook, we could use that on the test, but if we do it on paper, we can't.
You can use a paper.
Oh, okay.
Yeah. You can use everything but your phone and your neighbor.
Okay.
Again, I am never going to test you, well, only when I absolutely have to will I test you on what. Normally, I'm going to test you on why and how. And the why and the how, that requires a higher level of thinking that you're not going to get from a two-dimensional screen. You're going to see lots of whats. Like, okay, that's a what. The why and the how is what's important. All right, so now inside the atom, we have what are called subatomic particles, literally below the atom or smaller than the atom. And they are the nucleons and the electrons. The nucleons are the proton, which is chilling out with a charge of +1 and a mass of +1, or mass of 1. A neutron has no charge, hence neutral thing, neutron, and it has a mass of 1. And then those are the two nucleons, and then the electrons are zooming around the nucleus. Not at all like any of the models you see on up here or in textbooks or online. Electrons don't do that. They don't do that, and they even don't do that. They're kind of zooming around in a cloud, and we're going to learn more about how they actually move around the atom when we talk about, we have a unit specifically dealing with electrons. But all these models are broken, but they're models. That's just how models work. They're like, yeah, it's close enough. Now, if you remember the video that we watched yesterday, if the proton or the nucleus is right in front of you, where's the first electron? Yeah, about a mile away. It's really far. If your proton's a basketball or a tennis ball, then the nearest electron's like a mile away. It's really far away. Okay. The atom is mostly empty space. Did you know that space is also an empty space? In textbooks, there's like the sun, then there's Mercury and Venus and Mars and the Earth, and there's Mars, and there's the asteroid belt, and then there's Jupiter, and there's Saturn, and then your butt, and then Pluto, Neptune, and that's also wrong. In reality, like if this is the sun, there's Mercury. Over on the wall is Venus, and somewhere in like Arizona or Utah is Earth. That's how spread out the solar system is, and atoms work the same way. There's a nucleus way over there, like near downtown Boulder City. That's where the electrons are. So the atom is mostly empty space. All right. So now, normally, when we say an atom is neutral, we mean the protons and the electrons are the same thing. There's the same number of them. There's the same number of positively charged protons as there are negatively charged electrons. That's what we mean by neutral. All right, so there we go. Questions so far?
Will there ever be like a native atom with its more electrons than protons?
Good segue. Yes, those are called ions. So if an atom is neutral, if it is an atom, it is neutral. Atoms have the same number of protons and electrons, but if it is an ion, then there is a different number of electrons than protons, and they will have a charge. Okay? Ions have more or fewer electrons than protons, giving them a charge. If an atom gains an extra electron, this is what gets a lot of people. If an atom gains an extra electron, don't blurt this out, just think about it. Is that ion with the extra electron negative or positive? Give you 10 seconds to think about it. If an atom, which is neutral, gains an electron, does that ion become negative or positive? Okay. If you think it becomes negative, put your hand out like this. If you think it becomes positive, put your hands like this. So a neutral atom gains an electron, does it become positive or negative? Okay, this is why I ask it. We've got about a 50-50 thing. Electrons are negative. So if an atom gains an electron, it gains a negative charge and it becomes a negative ion. Okay? If an atom gains a negative electron, it becomes a negative ion. Now, the other side of the coin is if an atom loses an electron, it becomes a positive ion. Because you have neutral, which is 0. If it gains an electron, it's negative. Or neutral, if it loses an electron, it becomes positive. Remember that from 5th grade?
Yeah.
All right. If you're with me so far, give me a thumbs up. If you have questions, wave your hand around. Moving on. All right. So in addition to ions that are special, there's also a type of thing called an isotope. An isotope is an atom with, or actually isotopes are atoms with different numbers of neutrons. They have the same number of protons, but different numbers of neutrons. So for instance, all carbon has 6 protons. All of carbon. Every carbon atom has 6 protons. But some of those carbons have 6 neutrons, some of them have 7 neutrons, and some of them have 8 neutrons. The neutrons basically make up the different type of isotopes. Okay. When we're writing a nuclide or a nucleus, we write the mass above the charge. This is the mass of the helium atom, 4, because there are 2 protons and 2 neutrons, 4. This is the charge of the helium atom, because there are helium nucleus, because there are 2 protons in the nucleus. So mass of 4 from 2 protons, 2 neutrons, Charge of 2 from 2 protons. Mass over charge. Now, to reference this again, you can have a carbon. Got it. Okay. You can have a carbon with 6 protons, and if that carbon has 6 neutrons, what's the mass? You can just blurt it out. 6 plus 6 is 12. Yeah, 12. You can also have a carbon that has 6 protons, and if it has 7 neutrons, the mass would be 13. Then you can have a carbon with 6 protons, and it has 8 neutrons, the mass would be 14. This is referred to as carbon 12. This is referred to as carbon 13. This is referred to as carbon 14. And they're all handy. We use them all for different things. All right. Yeah.
So the bottom number is the protons, right?
Correct. Yep. Because keep in mind, it is the charge of the nucleus. The only thing in the nucleus that has charge are protons. So the charge comes entirely from the protons. And then the mass up top is the protons and the neutrons as a sum. Click, click, click. All right. So when things are radioactive, it means their nucleus has too much or too little of something. Okay. We say when nuclides decay, that's the word we use, decay, when they're radioactive, they are attempting to balance out their numbers of protons and neutrons. They've got too many protons or too many neutrons, or too few protons or too few neutrons. So they give off particles from their nucleus, or sometimes they even take in particles, and that makes them radioactive. In the video, they call them malcontents. It's a malcontent. It gives off alpha particles. Okay. And there are 3 types of nuclear particles we're going to talk about: alpha, beta, and gamma. An alpha particle is 2 protons and 2 neutrons. It is affectionately the helium nucleus. Is the alpha particle a helium atom? No, because an atom has a nucleus and an electron cloud. The alpha particle is just the helium nucleus. A beta particle is a high-speed electron, and a gamma particle is an electromagnetic wave. Think light beam. This is a nuclear equation. A nuclear equation is you have one nucleus breaking down into another nucleus and the particle that's left over. This is called the parent nuclide. This is called the daughter nuclide, and this is called the particle. So this would be read as uranium-238 becomes thorium-234 and an alpha particle. Or you might say uranium-238 gives off an alpha particle and forms thorium-234. You might notice right away, some of you are shrewd, that uranium is atomic number 92. Boop. Thorium is atomic number 90. Boop. Hence, the charge, which is the number of protons, will always match the atomic number on the periodic table. Let's say that again. The charge of the nucleus will always match the atomic number on the periodic table. What matches the atomic number on the periodic table?
Charge.
The charge of the periodic table, the charge on the nucleus, is the atomic number. So if you have an element and you're like, this is X2042, you're like, what element is that? There is no element X, by the way. That's why we use X. I'm like, 20. Okay. 19, 12. Calcium. X is calcium. So this is actually calcium 2042. Or calcium 42. Because the charge is the number of protons, and so that's the atomic number. All right. If you're with me so far, give me a thumbs up. If you have questions, wave your hand around.
Can you review the alpha, beta, and gamma
Sure.
rays?
Alpha particles consist of 2 protons and 2 neutrons for a grand total of 4 mass units and 2 charge units. 4 and 2, alpha. So 2 protons, 2 neutrons, grand total of 4 mass units and 2 charge units. A beta particle is a high-speed electron, so we effectually say it has 0 mass. We're going to talk about each individual one here in a second. And then a charge of -1. And a gamma particle is basically what's called an electromagnetic photon, which has no mass and no charge. All right. So let's talk about each individual piece. Again, this was also in your video, but I know videos go fast. So an alpha particle is a helium nucleus, has a mass of 4, charge of 2. And that mass of 4, charge of 2 comes from 2 protons and 2 neutrons. And those 2 protons give it a charge of 2. So some properties of alpha particles. Here's the good news. If you are in the environment and there is unless it's in the air, like a dust, and it's an alpha emitter, you're going to be fine. If the alpha emitter is a dust and it gets in your lungs, that's a bad thing. But alpha particles, if you had an alpha emitter, you could hold it in your hand and you're going to be okay. Because the alpha particles will get blocked by your skin. You will eventually feel a rash because the particles that are blocking the alpha, or the skin particles, the cells that are blocking the alpha particles will eventually wear down, kind of like getting a bad sunburn. But for the most part, you're going to be okay. Because alpha particles are really big and really slow. They move slowly. They just get stopped. They're like, Red Rover, send the fattest kid you got over. And you're like, he's so slow, he can't break through. And that's what happens to alpha particles. They're the slow, awkward kid. Red Rover, send the fat, awkward particle over, and it's not going to get through. And they do that, and they can't do that because they're so big. They're so big and they move so slow. But they do cause ionization. And this is a really important concept. So I'm going to pause for a second. Some of you are still scribbling. Ionization. At the front of ionization is the word ion. What's an ion?
A positively or negatively charged atom.
A positive or negatively charged atom. Something that has a charge. Ions are atoms that have a charge. So if you are chilling out, you're carbon-12. You're like, hey, I'm carbon-12. I make up the large portion of all the cells, and I'm organic matter, and all this is great. You got a mass of 12, which means you have 6 protons and 6 electrons. And then along comes an alpha particle. An alpha particle has a charge of 2, no electrons. So the alpha particle hits the carbon-12 atom, and it steals 2 electrons. Because an alpha particle has no electrons. It's only protons and neutrons. That alpha particle steals 2 electrons, becomes an atom of helium, leaving the carbon with a +2 charge. Let's do the math again. So if you're carbon, like, hey, I'm carbon. So carbon has a mass of 12 and a charge of 6. And the alpha particle slams into it, the protons are not going to change. Okay? Because it's still going to be carbon. However, if it also has 6 electrons, if carbon also has 6 electrons and it's neutral, and then the alpha particle hits it, it's still going to have a mass of 12 and a charge of 6. In the nucleus, the problem is now it only has 4 electrons. Because the alpha particle took 2 electrons. So 6 minus -2. -6 minus -2 is -4. 4. So now this thing has a +2 charge. 2 electrons were removed. Where there was previously 6 negatives, there's only 4 negatives. So it has a +2 charge. That's called ionization. Okay, and alpha particles, again, if you breathe in the dust of alpha emitter, you're going to be in really bad shape because they're going to start attacking the cells in your lungs. But on your hand, you're like, well, that's interesting. You can hold it there, and you're like, I don't even notice it. You know, maybe a couple hours, you're like, I got a sunburn. But that's ionization energy, or ionizing energy. All right, if you're with me so far, give me a thumbs up. Question.
So will the alpha particle always take just 2 electrons?
Yep.
Okay.
The question was, will the alpha particle always take 2 electrons? Yep. It's got 2 protons, 2 more electrons, and it'll balance out and become neutral. Yeah.
So the alpha has like 4 mass units, and that's 2 protons and 2 electrons.
2 neutrons.
Oh, 2 neutrons.
Yeah.
Okay.
So 2 protons, 2 neutrons for a total of 4. No electrons at all until it's sealed. Good questions. Any other? Moving on. Okay, beta particle. This is the cool one. All right, so beta decay is crazy. Beta decay is a high-speed electron ejected from the nucleus. A high-speed electron ejected from the nucleus. This should make some of you kind of a little confused. Because what's in the nucleus?
Protons and neutrons.
Protons and neutrons. And where's the electrons?
Outside.
Not in the nucleus. So it's really strange, and this goes to science and nuclear physics a little bit beyond the scope of this course. But it can basically be argued that a neutron is basically a proton plus an electron. Because a neutron has a mass of 1 and a charge of 0. A proton has a mass of 1 and a charge of 1. An electron has a mass of effectually 0 and a charge of -1. So it can be argued that a proton with certain nuclear models and an electron can form together to become a neutron. And a neutron can split into a proton and an electron, but that electron immediately gets ejected from the nucleus, leaving behind a proton. So what does that do? That turns a neutron into a proton. It turns a neutron with a mass of 1 and no charge, gesundheit, into a proton with a mass of 1 and a +1 charge. So the neutron with a mass of 1 becomes a proton with a mass of 1. The neutron with a charge of 0 becomes a proton with a charge of 1 because this electron gets created and then gets yeeted out of the atom. That's beta particle. Okay, so some properties of beta particles. They're fast moving. In fact, they move near the speed of light. And they're nasty. They blast right through things until something hits them. And then they are also ionizing because they're negatively charged. So you can block beta particles. Unfortunately, your skin won't, but your muscles will, or your bones will. The bones will block beta particles. Bing, 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 bing. Unfortunately, each cell that absorbs a beta particle is going to fall apart, or at least the protein that makes up that cell is going to fall apart. It's going to ionize. The crazy thing about beta particles is beta particles cause the atomic number to go up by 1. Because a neutron, which has no charge, becomes a proton. You increase the number of protons, you increase the atomic number. Because the atomic number is the number of protons. All right, how we doing? Okay. Good? Give me a thumbs up if you're with me so far. Okay, wave your hand around if you have questions. All right, so that's a crazy beta decay. Alpha, beta, oh, question.
So beta, like, when it interacts with an atom, it just makes it go up one charge.
Yes.
Okay.
If a molecule grabs a beta particle or a beta particle slams into it, it makes that molecule negatively charged. Ionizing radiation. It's not fun stuff. Pretty nasty, actually.
Wait, makes it negatively charged?
Right, because the electron is negative, the molecule will capture the electron, and the whole thing will become negatively charged. Because remember, an electron is negatively charged. If you add an electron to something, it becomes negative.
Wait, now I'm confused.
Okay, so the beta particle is a high-speed electron, okay? And there's proteins in your lungs that are just kind of chilling out, being proteins, doing their job. And then a beta particle hits it, it sticks to that protein, and that protein goes from being a molecule to an ion because the negatively charged electron has stuck to it, causing it to become a negative charged ion.
Okay.
Cool? Not fun stuff. Okay, and then there's the Hulk. The Hulk's blood is gamma resistant. He absorbs gamma radiation, which is all just bunk, because gamma radiation will blast right through blood. Okay, gamma rays are high energy electromagnetic radiation. They have no mass. They have no charge. Think of them as laser beams. Okay, can't see them though. Okay. So they're usually given off as spare change. Okay. You're being blasted with gamma radiation. Let me just skip that. Or you're being blasted with gamma radiation right now. You don't even realize it's just right through you. Okay. There's a small chance if a gamma ray hits your bones, it'll stop. If you have a titanium hip like grandma, then there's a good chance the titanium hip will block it. But other than that, most of the gamma radiation right through you. Oh, unless you have braces. There's a little bit higher chance that the gamma radiation hit your braces. But for the most part, it's going right through. It's going right through everything. It might get stopped with metal, but it's going to take a lot. Okay, now here's the thing. You guys know that opposites attract and likes repel. The single most important concept in all of science is opposites attract and likes repel. North and south magnets attract. North and north magnets repel. Positive and positive repel, positive and negative attract. So it turns out if you fire these particles through an electric field, the beta particle, being negative, will arc towards the positive plate, and the alpha particle, being positive, will arc towards the negative plate, and the gamma ray is going to go right through. A dude named Rutherford did this about 100 years ago. Big dude, Rutherford. He got an element named after him, Rutherfordium. Okay, so 3 basic types. Alpha, big ugly, gets stopped easily. Beta, you're going to need a little bit of metal, and gamma, you're going to need a lot of metal to block gamma. All right. Questions? Because we are about to change gears. Okay, so again, pay attention to this. This is the next one we're going to be doing. Nuclear equations. This is a nuclear equation. Uranium-238 becomes thorium-234 and an alpha particle, and then it's got a little spare change. We don't usually draw the spare change in the equation. You just need to know it exists. All right. Neutron emission, we can, neutron emission is basically just an ejection of a neutron, creates nuclear reactions. This is why nuclear reactions do what they do. I really need to get to nuclear equations. So not terribly important, but there you go. It's also in the video. It's what, to watch the video, it gets off neutrons. Each neutron causes something else to break. But this is what we care about, nuclear equation. Okay, so what I'd like you to do is get your slates and markers. If you need markers, I can throw some at you. And what I'd like you to do is, with me, we're gonna do the nuclear equation for sodium 24 undergoing decay. Oh, and if you need tissues, there's tissues over there. All right.
Yeah, I love that.
Nuclear equations. So sodium 24 undergoes alpha decay. So the first thing we need to do is write down what sodium's atomic symbol is. So sodium's atomic symbol is Na. Why isn't it SO? Because sodium was discovered before English was a thing. That's why it's Na. Sorry, I know it's hard to believe that English wasn't around for thousands of years, but it's really only been around for a few hundred. Okay, so sodium, the 24 represents the mass. So we're going to put the mass up here. And then all sodium have the same number of protons. So we go to the periodic table and we find that sodium has 11 protons. All right. That's sodium 24. Undergoes alpha decay, which means it is going to release an alpha particle, which is 4,2He. Again, the alpha particle is a helium nucleus with a mass of 4 and a charge of 2. So the sodium 24 releases an alpha particle, and you say, oh, what's left? Well, 24 equals 4 plus 20. 11 equals 2 plus 9. You see what I just did?
Yeah.
A little bit of arithmetic. And then you say, what element has 9 protons? You look on the periodic table. Fluorine. Yeah, just fluorine. Fluorine. This is a balanced nuclear equation. Sodium 24 undergoes alpha decay. Sodium has atomic number 11, so it has 11 protons, 24 mass units. It gives off an alpha particle, and what's left over is fluorine 20. All right, how are we doing? Can I tell you about a trap? The mass number, listen carefully, super carefully. The mass number on the periodic table is never the mass of the nuclear particle. The atomic number on the periodic table is always the atomic number of the nuclear particle. So you notice sodium is 23, not 24. But sodium is 11, is 11. The atomic number on the periodic table will be the charge of the nuclear particle. But the mass on the periodic table will not be. That's what we're going to learn about that in the next unit. All right. If you're with me so far, give me a thumbs up. This next one's for you. I mean, boop. Yes. Boop, 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 boop. There we go. All right. This one's for you. Remember, a beta particle is an electron. It has no mass, a -1 charge, and it's an electron like that. So go ahead and finish this one up. Do this while I do something else. I will be calling on a military volunteer, by the way.
Oh, what is iron? What's that? Yeah.
Okay, I gotta go away from this.
You write whatever beta is, which is like negative zero over negative 1. No, zero, negative 1.
Using a mouse.
But is it 53 over 131?
Oh wait. That's how we did the last one.
Then I.
So then it goes over here.
There's the mouse. Okay.
And then you just click it.
Wait, where'd you get the E? What is that? Oh, we put it up there. That looks right.
And then that adds one, right?
Like to get, yeah.
And so you're
54.
All right, here we go. So the following person is going to give us his or her answer.
What the heck?
It's been in for a long time. Okay, so what do you got? Show me your answer. So iodine 131 gives off a beta particle and produces xenon 13154. Got it? Do you agree?
Yeah.
Yeah, sounds good. So done. So Sophia. So who agrees with Sophia? Yeah, I think she did a great job. So iodine 131, beta particle, xenon. Ready for one more? No, please, no. He's gonna call on me. Oh, there's a 1 in 29 chance that's gonna happen. Tungsten is the W that used to be called wolframite. Now it's tungsten. Oh, hey, get back there. Silly. There we go. Get back there. There we are. Turns out dropping a mouse makes everything freak out.
So it's W, he said. So what's the atomic number? 70. What's the atomic number? 190. W. Arrow. And then where'd you get that? Why? How do you know? Who's wrote it down? That's all of us. And beta is that.
So then you subtract, so it's 186.
What's the first
72? What's 72?
Question or answer?
Question.
Okay.
So what's the atomic number that's
What's beta?
Correct. Yeah. So tungsten's atomic number is 74. So that's going to be 74 protons in the bottom.
Okay, and that does not So the electrons don't have effect on the combustion.
Correct. Everything we're doing is nuclear. All right.
That's not.
I don't know where I
All right. Looks great. So we have tungsten 190 is an alpha particle, and hafnium 18672.
Yes.
Sound good?
Yeah.
Yeah. Good job. All right. One more, then we're done for the day. So again, everything on top is going to match everything down below. 190 equals 4 186. 74 equals 272. Now a neutron is a single particle with a mass of 1 and a charge of 0. So that's what your thing's going to look like. Cobalt's going to release a neutron. Cobalt 60. A neutron has a mass of 1 and a charge of 0.
So it's 60 over. So we add them. Wait, what did I say?
Alexa, stop.
All right. Oh, I think whoa, why did it 69? Oh yeah, no, they said 59. That's what 59. Sorry. Wait, it was yeah. So brilliant.
All right. So 6027 cobalt, proton. 5927 cobalt. Sounds good to me. So, all right. Do you feel like you can do this on your own? Okay. So you have an assignment on Canvas to do that very thing. So completing the particles, and then there is a matching skills test on nuclear equations. Yes.
So what was the last? Oh, so a neutron. It released a neutron, and that's the thing for. Does gamma have one?
No, because gamma is always 0, 0. Technically, there would be like 2 gamma particles here, a gamma particle there, 3 gamma particles there. Yeah, gamma particles never actually show up in nuclear equations because they're spare change. I just have to teach them so you know what they are.
Okay, thanks.
All right.